Hello, my name is Leo Dorst, and there are some exciting developments in the computational representation of Euclidean geometry that I'd like to share with you in this talk. It's about PGA, plane-based geometric algebra. It is an algebra, but it's a practical algebra. It's a way of organizing your computations in geometry so that primitives and operators are nicely integrated in a way that actually makes them very suitable for implementation on GPUs. We have universal operators called motors that can move any primitive or motor in exactly the same way, exactly the same instruction, which enormously saves codes. These operators can be generated directly from the geometry. So for instance, if I want a rotation operation that rotates around a line L with an angle phi, then I can just do the exponential of that line as an object times phi. We have simple expressions to combine geometric constructions. So if you have a point and a line and you would like to plane through both, then the dot product of the line and the point is that plane. All this is coordinate free and can be specified quite generally in less code, just because the universal operators require only one line to state what they should do, which moreover can be implemented to execute more efficiently than homogeneous coordinates or dual quaternions. As a geometric algebra, the PGA is organized rather unusually to what you're used to. Normally you would define geometric objects first and then define the operators. Here it's the other way around. So like any geometry, the motions, the symmetries define what the geometry is. We generate the motions as multiple reflections. For Euclidean geometry, that means multiple reflections in planes, because two parallel planes give a translation, two intersecting planes give a rotation around the intersection line. And that means that algebraically we're going to have to let the geometric algebra work on a space of which planes are the vectors. It's a linear space with a dot product. We call it PGA for plane-based geometric algebra. When we look at that in detail in a few slides, we'll see that the fact that we want reflections motivate defining a specific product, a geometric product. That makes that a very straightforward thing to do. And then we find that the geometric product is also capable of intersecting elements. We already had the planes as reflectors. Now we get the planes to intersect to become lines and points. So those are the constituents of making objects in the geometry. And in this way, from motion to objects, we see that the motion representation dictates the object representation. The objects can then in turn be used to parameterize the motions, like we've seen that the rotation around a line is just the exponential of a line. And the consequence is that all the elements that we need, all the things we need to do Euclidean geometry are present in an integrated way. A little demo might illustrate this. So we're going to see a tricycle move. The tricycle is determined by the fact that it has a rear axle and a front axle that can be steered over this angle. When they intersect, they create the point around which the rear axle rotates when it moves. And in geometric algebra, that'll be just an operator that computes the intersection. It's the product. Then the exponential to make the motion, and then the motor, the motion operator, can be applied to any element of the body of the bicycle, the vertices, the edges, the planes, the texture, and they all move in exactly the same way. And when we see it move, you will see that as the rotation angle changes from straight to left to right, there's just no singularity. If this intersection is an ideal point at infinity, the exponential of an ideal point will turn out to be a translation. So we're first going to see how we have to represent motions. And this is the basic principle behind it. We are going to map our present world into a representational space in which the motions are represented as multiple reflections. That means that in that space they are orthogonal transformations, they preserve the dot product. And we are helped by a theorem by Cartan and Dieudonné that if we have an n-dimensional symmetric bilinear space, then all the orthogonal transformations in that space can be generated from reflections. So once we're into orthogonal transformations, this is the general principle. Reflections are represented normally by this formula here in linear algebra. Let's see how it comes about. You have a vector space, so you have a vector. There's a plane in this space with a normal vector A. You'd like to reflect this vector in the plane. What do? Well, a role is being played by this projection of x onto A, and you have to subtract that twice from x to get to the reflected vector. So this is the operation, x minus 2 times, and this is the projection operator. If this is a unit vector, it just is x dot A times A. If it's not a unit vector, we have to divide by a norm of A squared. Now this is a formula that you cannot really use to organize your motions. It's just too involved. But that is due to the occurrence of the dot product. The dot product is symmetrical, and the idea by Clifford was to replace the dot product by something that you say it's the symmetrical part of a deeper product, and that deeper product is called the geometric product. It is denoted by just a space. And so if we take xa plus ax, that's clearly symmetrical, divided by 2, then that is what the dot product is. Okay, so if we substitute this equation into that, we find that here we have that replacement. We now are assuming properties for this new product, that is distributivity and so on, so that we can expand these terms, and we get 3 terms. The first one is x, the second one is this. But a squared divided by the norm of a squared, the norm of a squared is a dot a. And you see here that this is the new product squared. So this equals 1, and these two terms cancel. And then we have 1 term left over. Well, by what I just said, you can see that the inverse of a vector a is a divided by a squared, because if I multiply this by a, I get 1 again. And so this is the inverse, and we are left with a much more simple formula than this one, namely a sandwiching of the thing we want to reflect between the reflector and its inverse with a minus sign. Otherwise we get this reflection. Now, why is this handy? We want to do more than one reflection because we want to make all the orthogonal transformations. And if we start with this one and we put it inside another reflection, then things get to organize. The minus sign cancels. Here I have BA, and here I have BA inverse, really, because the inverse of a product is the product of the inverses in opposite order. If I put on my socks and then my shoes, then I have to first take my shoes off and then take my socks off to get back to the normal situation. Okay, but we also know from geometry that if we do a double reflection of an x in 2 planes, and this is the first reflection in the blue plane, the second reflection in the green plane, then what I've effectively done is I've ended up at the place that is achieved by rotating this vector in the common line of the planes. And if A is the normal vector of the blue plane and B of the green plane, and they make an angle phi over 2, then I will end up at an angle phi. So I have a rotation operator. It is again sandwiching, now without the minus sign because they got cancelled. So an operator and its inverse, and it's a rotation in 3D around a line through the origin. Therefore it must be isomorphic to a quaternion, and indeed it is. But quaternions we're used to are complex things, and this is all completely real. So that's nice. In our real vector algebra, there is a geometric product, which when applied in a sandwiching operator gives us the same as having done weird things like complex numbers for rotations. So that's the principle. We are going to do multiple reflections, but not just in the origin. So now we have to find out if this is the general principle by which geometric algebra can generate reflections using vectors. Then we need to be in a space in which our vectors are what in our real world are planes. Two planes, two parallel planes translation, two intersecting planes of rotation. And that'll be handy because, as we see, we will have a really nice representation of orthogonal transformations. In linear algebra, you wouldn't even think of this because orthogonal transformations are a difficult kind of matrix. For us, they will be a simple kind of operator. Now you already know how to represent a plane as a vector. Homogeneous coordinates has something like that. You take the normal vector of the plane and you slap on something about the distance to the origin, and this is made in such a way that if you take the dot product of this with the representation, homogeneous representation of a point, you retrieve the plane equation x dot n equals the distance at the origin. We put a plus sign here too, because we can choose our units. So it's 3 Euclidean dimensions to indicate the normal vector and 1 extra dimension here with basis vector e that does the embedding. So we're in a 4-dimensional space, and we therefore expect that according to Cartan-Dieudonné, that 4 reflections will generate all our orthogonal transformations. To make reflections, we need a metric, and we need to specify therefore what it is to take dot products in the Euclidean part of the space. Well, that's easy. E1 dot E1 is 1, E1 dot E2 equals 0, etc. But we should also say what the extra dimension does, and we make it orthogonal, so E dot E1, E dot E2, and E dot E3 are all 0. It's really an orthogonal part of space. And we have to do one little special thing. We don't want to see epsilon squared when we start squaring planes, because we don't know how to interpret those. So epsilon dot epsilon, or E dot E, I should say, should be 0. And that's it. So we have a metric space with this metric. It's 3 Euclidean dimensions and 1 dimension that squares to 0. Now let's see whether it works. So we are going to do a double reflection in 2 parallel planes with normal vector n, and the second one is at a distance delta over 2, because we know that as we reflect, we double the distance, right? So, just like when we reflected into planes, we doubled the angle. And if we perform this geometric product, then we see we get n squared, that's here. We get en delta over 2. We know that, let's say that we have normalized these planes to be planes with unit normal vector, then n squared equals 1. And then this is precisely the translation vector over which we would like to move. And because, so this is already our translation motor, translation operator, we can also write it in exponential form, because if we see this as a series, we can develop this as 1 plus this thing squared, but this thing squared is 0 because e squared is 0. And I have a minus sign here because I swapped those 2 terms. That's the conventional way of representing it. Same thing with rotation at the origin. I take a plane in direction, normal vector in direction E1. I take a plane with a tilted orientation over phi over 2. I perform the product and I get E1 E1 times the cosine, E2 E1 times the sine. I know that E1 E1 equals 1, so this is a scalar. And I don't know how to simplify this, so I just give it another name. I call it I. It's sort of related to that plane that I'm rotating in. This basis was chosen completely adapted to the plane. Right? It'll be in general situation normally. But there's something special about this I. It was E1, E2. If I multiply this out, then I see that I can, because the dot product between E2 and E1 equals 0, E1, E2 and E2, E1 have a minus sign relative to each other. And then I can put the brackets back in. I get e1 squared, e2 squared, they're both 1. So because of that minus sign, I have I squared equals minus 1. And that means that I can also make an exponential notation for this thing, because as I develop this exponential in a Taylor series, I get terms with I squared, which gives me a minus sign, I to the third, which gives me I times a minus sign, all precisely right to allow me to write this expression just as you're used to in complex numbers. Now I've chosen a special basis. Normally that plane would sit askew from the regular world coordinates that I want to introduce. So E1 and E2 will be linear combinations of E1 world, E2 world, E3 world. That means that I will get mixed terms from in world coordinates E2, E3, E3, E1, and E1, E2. So this really is a vector with components on this basis. The basis elements each squared to minus 1 in the way that I've just demonstrated. And so what I have here is a unit quaternion, but I've made it as the multiplication of two real planes. The operators we have should be applied in a sandwiching manner. So an object A will be translated or rotated by a motor M in this manner. If we now have a composite object that consists of A and B, then something really nice happens because of that sandwiching form. Here we see the composition of the moved A with the moved B, with here a composition operator is a geometric product. And because this and this cancel, due to the associativity of the geometric product, we can actually move the motion completely outside. So we could also have made the composite object AB first and then moved it. Now, and this is really the crucial reason of why we have the motion representation we have. We have a two-sided representation that has this property. As long as we make compositions out of geometric products or linear combinations of geometric products, we will always have that things transform in a covariant manner. Whether we move them first and then compose them, or compose them and then move them, it makes no difference. That means we don't need a method for every kind of object that we construct. Lines transform in exactly the same way at the points and in the proper way. If you would have made the line out of points and moved those, you would have gotten exactly the same motion as moving the line directly. That means that there's no need for a lot of code because all things move the same, and that prevents a lot of bugs. And in fact, this structure is very suitable to put in the compiler and have it generate coordinates code for the things that you want to move. You will know that it is correct. Okay, so those are the motions. Now let's go to the primitives. We've used the symmetric part of the geometric product already, when we defined the geometric product in terms of the dot product. But that leaves a part left over, and that's the outer product or the wedge product, which we denote like this. And it's the antisymmetric part of the geometric product. And it turns out that this is precisely the right way of spanning things in the regular geometric algebra around the origin, but that in our representation of planes, it's actually an intersection operator. So the line common to two planes will be the wedge product of the two, and it may be an ideal line. If the planes are parallel, then we get a line at infinity, which will be very useful. It's certainly not exceptional. It's just an element of the algebra. And a point common to three planes should be the wedge product, the intersection of three of these planes. So let's make a point. We take a plane with normal in E1 direction at the location x1, normal E2 at location x2, normal E3 at location x3. That should be the plane at the location, the point at the location x1, x2, x3. When we multiply it out, we get something like this. And we indeed see something that has component 1. We see something that is a multiplication of x1, x2, and x3. But we see that the basis on which these are expressed are these trivectors, as we call them, composed of these different things. For an implementation, this is still homogeneous coordinates, but the integration with the rest of the system enforces that we should see it as a trivector on a trivector basis. So that means that we're getting elements that reside on a basis of scalar, of the vectors. Those are the planes. We have made lines through the origin. When we made the quaternion, we saw that we get things like E1, E2, E2, E3, E3, E1. So those are Euclidean bivectors. We also get components that involve that extra dimension E, which is indicated by a knot here to indicate the pattern. We have just seen that we made points on a trivector basis, and we can go one further. We can also have what's called a pseudoscalar, which is basically the volume element of the space, all of them involved. And what we've also done is we've made a rotation operator as a quaternion that was in this space. We have made a translator which involves these elements. And if we make a general motion, we would multiply this with that, and we get any element out of this total group. And that is, as we'll see, a dual quaternion. So for a three-dimensional space, we have a 16-dimensional basis. But we're using everything. We even recognize everything. We even see some things that overlap in usage, like line elements are part of making a rotation operator. They're all related by the geometric product, sometimes specialized to the dot and the wedge for intersection and projection, but they're all consistent. And if we multiply out all the elements, we get multiplication table. But what I want to emphasize is that it seems like a lot. It seems like we're introducing way too much. But since all these elements are already things that you're using in your code, this structure is there. It's just hidden, and you have to reinvent it all the time. Now we've made points by intersecting three planes. We can also make lines by joining 2 points. That is another operator. It's called the join, and it is defined in a dual way to the wedge operator. It's like a Boolean way of saying that if you intersect 2 orthogonal complements and you take the orthogonal complement, then you have the connection. So this is also an operator, and we can show that we can write this out as a linear combination of geometric products. So this is also a covariant operator. I'm allowed to join the 2 points and make a line and move that line either by moving the 2 points and rejoining them, or by just moving the line directly. If you do it more carefully, you find that these homogeneous factors that we have ignored so far are actually very useful. You can make measures that clearly have an oriented nature with odd angles, in the sense that if the line and the other line meet in this way, intersect in this way, well, they don't intersect, but we get something that is proportional to the distance and the angle of their direction vectors. And as we move this line to the other side, the distance changes. If we change the angle of the relative orientation, then the distance changes. We can make consistent orientation measures so that you don't really need to guess the signs afterwards. You can set them up consistently, and the GA computes with them for you. We also need to measure things. If we use the regular norm that we're used to in geometric algebra on these elements that contain E, the thing that squares to 0, we find that we only get the norm of the Euclidean part. So we introduce an extra norm which can measure the size of the E part, because that also turns out to be relevant in some computations. And Stephen de Koning really recently found a very nice property that if you take an edge loop, a set of connected edges, by connecting points consistently from one to the other by the join operator and getting weighted lines, then the contour length of this edge loop is the sum of the line lengths, not surprisingly, and the area is the infinity norm of the summed line objects, the summed line bivectors. And this even generalizes to 3D, where you have a facet mesh where you connect your points in a consistent oriented manner in facets. Then the area is the sum of the sizes of these elements, of these plane elements, and the volume is the infinity norm of the summed elements. So this is very nice, and we're discovering more simple operators to use in this manner. Now we have all these elements. For instance, here we have a red plane and a red line. That's not so clear to see, but that's here. All these other elements are completely defined in a coordinate-free way in terms of these basic things L and P, this bivector and vector in the geometric algebra. So for instance, in the intersection point, that's somewhere here, is the wedge product of the two. This is a vector, that's a bivector, together a trivector. It must be a point. It turns out to be the intersection point. If I want the perpendicular line to this plane through that intersection point, then that is L wedge P divided by P. If I want the projection of the line onto the plane, that is this operator, P dot L divided by L. If I want the projection of the plane onto the line, which is the blue line, we would normally not call that a projection, then it's just L dot P divided by P. So there's a straightforward structure which can be learned and understood, and we've made a cheat sheets of the operations we're beginning to find that work really nicely to fill needs. All right, that was geometry. Now let's see how far we can get into physics. First, we look at the line parameterization that we have with bivectors. You may recall that we had this in the situation where we looked at the origin and we encountered our first quaternion, and we had this as E1, E2 in a general geometric algebra. But in PGA, we would recognize E1, E2 as E1 wedge E2 as the meet of two planes. So this is really the line through the origin. So we have a rotation through the origin characterized by its line. If we now use covariance, that means we go to an arbitrary line that is a distance P from the line L0, then we can apply that operator to that translation to the operator. Because of covariance, we can lift it into the exponential. We see that we get the line L, and so we have a full parameterization of an arbitrary rotation around an arbitrary line, just as the exponential of that line. Then going to general motors, we need an extra translation because it's not just rotations. We then get the exponential of a general bivector, as we would call it algebraically. Geometrically, we would more see that like a screw. And then we have a dual quaternion. But again, it is generated by, in principle, 4 reflections, or 2 of these operators that we've seen here before. And they all have the form of the exponential of the invariant. So here the line is invariant, the exponential of the line is the rotation operator. If a direction is invariant, the exponential of the invariant is the translation operator. And these are precisely the constructions we used in our demo. So we had 2 lines in 2D, they wedge together into a point is the invariant, and the exponential of the invariant is then the motion operator that we can use on the tricycle to move it around in the orbits. No exceptions, it's just done. So motion is characterized by bivectors as their exponential, and bivectors are therefore important to describe it. Now when we then go to the classical physics description of, say, kinematics, then we need the momentum. The momentum is a point moving with a certain velocity. And if we make the bivector the line of the point with its velocity, weighted with the mass, add those over all the points of our object, we get the total momentum. Now when we implement that in PGA, and we have it moving with a bivector B, then we find several components. One is how the centroid translate, and the other one is the internal rotation, a purely Euclidean thing. This is the Euclidean part of that, and this is the other part. And it's weighted by this I, which is now the pseudoscalar of PGA, so it's E0, 1, 2, 3, a thing that squares to 0. Looking at dynamics, we need to talk about forces. Forces are attached in a certain direction to a point. If we write that out, we find again a natural split into something that is a force and a torque. Then moving to the Euler equations and the Newton equations, for translation and for rotation, we actually find those as two components of one bivector equation, which just says that the derivative of momentum is the force, and we are now working on integrating those simultaneously in one go by RK4 methods, and you may expect a write-up about that fairly soon. So that's the structure of geometric algebra, PGA in a nutshell. We have a 4-dimensional space with a 16-dimensional basis. These basis elements are all recognizable as either geometrical objects or as things that compose to operators that are isomorphic to efficient representations we already knew for these things, but are now completely, in a real manner, integrated with the primitives that they either work on or are defined by. And Stephen de Koning found that you can arrange these things in a somewhat strange fashion, where the things that you need for something are always in groups of 4 closely together in your memory. This makes for really efficient GPU implementation of this structure. It's being executed by Jeremy Ong in his program Klein, and he played some more tricks, Stephen. He changed the basis vectors slightly to prevent all sorts of extraneous signs that might not be the same for each group of 4, and gave additional efficiency out of that. Now, if you're already somewhat familiar with geometric algebra, you may know that we've been talking about conformal geometric algebra a lot. That is a geometric algebra that doesn't have planes as vectors, but spheres as vectors. And if you do multiple reflections in spheres, then you get something that is conformal geometry, but planes are also spheres. They're spheres through infinity, and therefore Euclidean geometry is included in this. And not too long ago, that was the only way we knew how to do it. Now, the restriction to just using planes is a nice subset of CGA, so it is completely compatible. If you have a problem in which you do not require round elements like the spheres and the tangents and the circles and so on that are in CGA, then you can use PGA for your application. If you then suddenly have need of a sphere, you just add one extra dimension, the extra dimension that is relative to CGA from PGA, and you have those as well. And we have some applications in robotics for that. This relationship between PGA and CGA has nicely been written up by Chris Doran, and I give the link here. Okay, maybe you want to know more. I wrote a tutorial, PGA for CS, for computer science, with especially a computer science audience in mind, and some demos. We have the cheat sheets, and we put presentations from various conferences that are worth seeing again, all on this website bivector.net. You can play in JavaScript with PGA and many of the other geometric algebras, and get a feeling yourself for how short the code is and how surprisingly efficiently it works. Thank you.